Right. So we are looking at this particular problem in the last lecture. Right. Something like this. So this was coming at a speed v naught, and these two were at rest, identical spheres. And we wanted the situation where coefficient of restitution is 1 for A and B as well as A and C's impact. So we wanted to find the final velocities. So let's begin with this part.
So we're supposed to find VA, VB, VC in terms of V naught, right?
Yes, yes.
So can we try solving this question this way, that we treat VC as one big ball, and so it won't have the same mass.
You can do it that way. Then you'll understand that after impact, the center of mass of B plus C will have what kind of velocity? A velocity along the x-axis only.
Yes, sir.
But it may not be necessary to complicate things so much.
Yes,
Okay,
sir.
see, we had seen that, see, when E was less than 1, A was stopping, right?
Yes, sir.
That we've already seen in the last. So we can now make a guess that if E is equal to 1, most probably what is happening, A is recoiling. It's going backwards, isn't it?
Sir, if the mass of B and C was half of mass of A, then it would be better to treat them as one object, right?
It's not so much about the mass, okay? You can treat them like one object. There's no problem as with that. But then what will happen is you're just complicating the problem, no? Because you will find the velocity of the center of mass of B plus C. But then you have to find the individual velocities of B and C also, no?
Yes, sir.
So it will become a two-step problem, no? Whereas right now you can keep it as a one-step problem in that sense, okay? So the collision impulse between A and B is acting along this line. So obviously B will have a velocity along this direction. Okay. And the collision impulse between A and C is acting along this line. So obviously C's final velocity will be in this direction. Okay. Now everything is symmetric. Both the coefficients of restitution are same. So we can see by symmetry what will happen. VP will have the same magnitude as VC. Okay. Which means that the impulse on A is acting symmetrically now in this direction and this direction. So the net impulse will be along the symmetry line. So from that we can say that okay, A's final velocity will be in this direction along the bisector.
Yes, sir.
Okay. So once we know that symmetry and we already know this angle and all that, so we can see over here what is the condition. The system's momentum has to be conserved first of all. Okay. So MA V naught as a vector has to be equal to the vector sum of all these. Okay. So let us take mod of VB equal to mod of VC as V2, and let's take mod of VA as V1. So we have minus MV1, okay, plus 2MV2 cos 30 degrees is equal to MV0. Okay, this is what the conservation of momentum will give us.
Yes, sir.
So we have root 3 V2 minus V1 is equal to V0. It's like our first equation. And we have two unknowns now, V1 and V2. So where the second equation will come from? From the coefficient of restitution?
Yes, sir.
Okay, so just apply that now. So this is coming from conservation of momentum. And E is equal to 1 for AB or AC, whichever you apply it. So velocity of separation should be equal to velocity of approach. Okay.
So we get the same equation.
We get the same equation as in?
Sir, the one we got from conservation of momentum.
Really? How come? Okay,
So,
what is the separation velocity?
sir, VB plus VC cos 30 plus VA.
It is VP plus, just for one pair, na beta. Just one of the two pairs.
Yes, sir.
Got it now. So how much it will be? This component of VA is a cos 30 component, right? So for example, if you look at A and B's separation velocity, it is VB plus VA cos 30, na?
Yes, sir.
And if you look at the approach velocity, how much was that? That was V naught cos 30.
Sir, only we not, right?
No, because see, you have to understand that V naught is in which direction? It's not in the direction of the center of mass of B, na?
Yes,
It
sir.
is the component of V naught in this direction, na? This is before impact.
So can we conserve kinetic energy for individual collisions?
We can do that also. We can conserve the total kinetic energy of the system. Or yeah, you can say that the kinetic energy of A plus B okay as a pair. No, here we'll have to conserve the kinetic energy of the whole system. Okay, A plus B plus C, that kinetic energy will be conserved because both of them are perfectly elastic. Okay. Right, so what is the approach velocity? It's V naught cos 30, right? So the other equation that we have is that this VB we have taken as V2 now. Okay. So V2 plus root 3 by 2 V1 is equal to root 3 by 2 V naught. Now this system has to be solved. So what we can do here is equation 1, and we can take equation 2 and multiply it with root 3. Okay, so we'll have root 3 V2 plus 3 by 2 V1 is equal to 3 by 2 V naught. And now we can subtract these two equations. So that will give us 5 by 2 V1, right, is equal to V naught by 2. So V1 interestingly is coming out to be V naught by 5, which means that V2 will be V naught plus V1, so that's 4 by 5 divided by root 3. Okay, so hope the concept of application of approach and separation velocity is clear to all of you here.
Yes, sir.
Sir, V2 will be 6 by 5 root 3 V naught.
6 by 5 tak, yeah? Okay, I'll just check. So V2 is V naught plus V1 by root 3. Oh yes, yes, sorry, it's not minus, it's plus.
So noted.
Right. So this is clear.
1 second, sir. 1 second.
Hmm. So now you can also check that if you look at the total kinetic energy of the system, finally, it's basically half mv1 square for A plus 2 times half mv2 square for B and C. You check that will come out to be half mv naught square. You put these values.
So there are no such questions in HCV with multiple particles.
No, HCV is this thing exercise of system of particles, as well as the next chapter, rotational mechanics, is a bit limited. These are the two chapters so far in which, actually, even to a certain extent, relative motion, HC Verma has limited types of questions. So you have to solve the module
Okay, sir.
along with HC Verma as your first, first sort of exercise in system of particles. Then, of course, I'm going to be sending some revision worksheets also. Okay. And along with that, once you're done with all this, there is always DC Pandey and Cengage. So DC
Okay.
Pandey has a very extensive set of problems. Okay.
Okay, sir. So noted.
Right. So people done with this now. Okay. Now we will move aside from collisions and look at some additional types of situations where we apply concepts from system of particles. Okay. Before we finally come to variable mass systems, which is going to be a different aspect of application of system of particles. Okay. Now we'll just go back to one type of question that we have seen earlier, and now we'll understand that question in a different way because we have done collisions in detail. So you'll remember that we had done this type of problem earlier, where there was a spring involved. Okay. Now suppose I take this situation that this is a block of mass 2m with a spring attached of constant k, and this is at rest initially. And this one, suppose, is a block of mass m and is coming at a speed v0. Now if I ask you, find first of all the final velocities, that is after the spring eventually disengages from the block E. This is the block E, this is the block B. Okay. And I also ask you that the maximum compression of the spring and all that. So you remember how we had dealt with this question earlier? Okay.
Yes, sir.
Let's say we are given some values also. M is suppose 3 kg. So 2m is 6 kgs and the spring constant is, let us say, let's take this as 18 newtons per centimeter. And let's take V0 as, say, 6 centimeters per second and all that. Okay. So how we have done this type of question earlier by using this standard equations of energy conservation and momentum conservation, but energy conservation involves the potential energy of the spring also, right?
Yes, sir.
And then for the first part, where we are calculating the final velocities after the spring disengages, the spring has come back to natural length then. So in the energy conservation equation, we used to put x as 0 and solve it, right?
Yes, sir.
Okay. So, so work this out and tell me how much the answers will be. Okay, so this was the general method of solving it. That after some time, if these have velocities v1 and v2, momentum conservation and energy conservation. Okay, so for the first part, solve equation 1 and 2 when x is equal to 0. Okay, so the spring has disengaged. And for the second part, what is the special condition for x to be maximum? Their relative speed should become 0. Right. Excuse me. Okay. So for the first part, yes, that's correct. So for the first part, when we are solving for the final velocities of A and B after some time, that's like this situation. When they've kind of lost contact with each other again. Okay, so that time this is so if you compare this picture with the first picture before impact, then you're seeing this is what is happening. Okay. So can we not say that VA is going to be M minus 2M upon M plus 2M into V naught, and VB is going to be
Sir, how can we just ignore the spring?
because the spring is disengaged, na beta? So X is equal to 0 na, in the second part. When the spring is disengaged, X is equal to 0 in equation 2 na. So it's kinetic energy conservation.
So, but it was there during the collision.
So that is the point na. So the spring compresses all the way to whatever the maximum compression is, and then what happens? Then they start separating na.
Yes, sir.
V2 becomes, so as they start separating at some stage, the spring disengages.
Yes,
So
sir.
at that point of time, what has happened? Its kinetic, its potential energy has become 0 again.
Yes, sir.
So actually, if you see the whole sequence of events happening from this picture, the initial picture before impact, to the final situation, it is basically what? It is a perfectly elastic collision happening in slow motion.
Yes, sir.
Okay. So before to final, this is a perfectly elastic collision. In sort of slow motion. And that is why it is perfectly elastic, because the spring provides the elasticity. It is able to temporarily store some energy as potential energy instead of dissipating it as something else like heat and sound and all that, and then re-engage it as kinetic energy. Okay. So that is what you'll get if you solve it this way also. You have V1 plus 2V2 is equal to V naught from equation 1, and we have V1 square plus 2V2 square is equal to V naught square from equation 2. If you solve these, but only thing is you will end up solving it as a quadratic equation. Or you can do this, you can solve it like this. V1 square minus V naught square, or rather the other way around. Two V2 square is equal to V naught square minus V1 square from equation 2, and 2V2 is equal to V naught minus V1 from equation 1. So just divide the two equations. So you can see V2 is equal to V naught plus V1, or V2 minus V1 is equal to V naught. So your separation velocity is equal to your approach velocity.
So written.
So even when two ordinary objects without any spring and all involved, when they make a perfectly elastic collision, what happens is as the collision is taking place, they are about to come in contact, then something like this actually happens. They distort in shape. So that time, the elastic potential energy becomes maximum, and kinetic energy of the system at that stage becomes minimum. And eventually they come back to their natural shapes. And again, the potential energy becomes zero. So kinetic energy is equal to initial kinetic energy.
Okay, sir.
But only in this kind of collision, this whole sequence of events is happening very, very fast, while they're only for that short duration of time they're in contact. Whereas the example we have imagined here, you will actually be able to physically track how the spring is compressing and then relaxing, because it's somewhat slower. Okay, so the second part we cannot solve by using the direct equations of collision, because it is happening while the collision is still in progress, it is not completed. So for the second part, we have to substitute V1 equal to V2 when x is equal to x maximum. So from equation 1, V1 is equal to V2 will be equal to how much? V0 by 3. Okay, and substitute this in equation 2. So this becomes V0 by 3 whole square into 1 plus 2 plus half k by m. Oh, sorry, I have cancelled the half. So k by m x maximum square is equal to V0 square.
So we got that V0 by 3 from the conservation of linear momentum, right?
Yes, from the equation 1. So put V1 equal to V2 in that, right? So
Yes, sir.
so now from this you can see that this is becoming V0 square. So this term will become 1 by 9 into 3. So that's 1 by 3. So 1 minus 1 by 3. This side, right? So this will give us x max as V0 into square root of, which is 2 by 3. And then we can substitute the values.
Sir, it should be V0 square into 1 minus 1 by 9, right?
Yes, what was the question?
Sir, this should be V0 square into 1 minus 1 by 9.
No, beta, there is the 1 plus 2 in the bracket, na? See on the
Acha.
left hand side. So it's V0 square by 9 plus twice of V0 square by 9, because there's the kinetic energy of M2 also, na?
Yes, sir. Sir, X max is V0 by 3.
Okay. I mean, it will have a unit, no, which you'll have to take care of, because I've given the units in centimeters per second and Newton per centimeter and kilograms. So you'll have to be careful about the units. You
Yes,
can
sir,
give
sir.
you can give V0 in centimeters per second, okay, but the K you convert so that you get that square root of 2m by K in seconds. You understanding my point?
No, sir.
See, if you were to convert this to SI units so that you get X max in meters, you would be doing this. Right, so that we get this in meters, right? So this would be 1 by 9 into 10 raised by 2. So its square root would be 1 by 30. So 1/5 of a centimeter. That would be our X maximum.
So noted.
Right, so hope this is clear, everyone.
Yes, sir.
So now we look at another variation of this kind of situation. So this was to illustrate actually that how we can almost create a perfectly elastic collision as long as we have an ideal spring and a smooth floor. Okay, now let's look at a variation of this situation. So we have a combination of three objects like this. So initially B and C are at rest. And also the spring is relaxed. Okay, but this is coming at a speed of V0. So now what happens is A makes a head-on collision with the block B with a coefficient of restitution of 2 by 3. So we want to find VA and VB just after impact. And then we want to find the maximum compression of the spring and also VB and VC, when this is the case. Okay. And we want to also find eventually the maximum value of VC. Here the spring is attached to both B and C. Okay.
So when they say just after the impact, it means the spring has not been compressed at all.
Okay, people, I'm going through the answers sent. Now, the thing is, what we have to understand is that the collision between A and B, even though there's the spring attached from the other side, is going to be almost like an independent event. Because what happens is that A and B's collision is going to be very fast. The time of contact is very short. And during that much time, the spring hardly, reacts in that sense. It takes a longer interval of time for the spring to start compressing. So the event of collision between A and B is so fast that it's like the spring hasn't got the time to react before that collision is over. So we can treat the collision between A and B like an independent event, like the first event. And then from that snapshot onwards, when the collision is over between A and B, then it's become a situation where B has got some momentum and the spring now starts to compress.
Sir, are you able to see my answers?
Yes, I'm going through all the answers sent by you people. There are some 4 or 5, so I'm going through it. So yeah, Janvi, I'm going through your answer. So 5 V naught by 6 is the velocity of which one?
The B.
B, just after impact. Okay. And what about A's velocity just after impact?
0.
No, beta, it's not a perfectly elastic collision, ना? तो कैसे 0 होगा? And 5 by 6 is also, okay, let me check. Yes, Siddharth, your answer is correct, I think. 5 by 6 part is correct, Janvi, but A's velocity just after impact. So
Yes, sir,
you
I
understand, we'll treat A and B's collision like an independent event, okay? So just after the collision is over, it's like B has got some velocity V2 and A has got some velocity V1. Okay, but the spring is still at natural length. It's not yet got the time to react. Okay, this is just after impact. So C is at rest. Okay, so the collision between A and B is like this, that VA will become M1 minus E M2 na, divided by M1 plus M2 into V naught, and VB will be 1 plus E upon M1 plus M2 into V naught. So this is basically 1 minus E by 2 into V naught, and this will be 1 plus E by 2 into V naught. So E is 2 by 3 here. So this is V naught by 6. Okay. And this is 5 by 6.
Yes, sir. By mistake, I left the V naught E and A while calculating VA.
Right. Okay. So now you understood now. And VC is 0 at that moment. So these are the values of VA, VB, and VC just after impact. Yes, Aryan, correct. Okay, so now that the collision event, okay, just a moment. Now that the collision event is solved, okay, so next up we'll understand that how the spring is interacting in between B and C. Okay, so once the collision is over, now A is not going to have any further involvement with the system of B plus C. So from this picture now, after some time, we reach this situation. So now we can see that in general, we take this as a closed system. So we have mv1 plus 2mv2 at any point of time is mvb just after impact. And we have the total energy of the system is just the kinetic energy of B just after impact. Okay, so these are our two general equations. So when X is maximum, V1 is equal to V2. Okay, so from equation 1, is that same kind of thing. Okay. So V1 is equal to V2 will become VB by 3, and VB was, remember how much, 5 by 6 V naught. So it will become 5 by 18 V naught. Okay. And substitute that in equation 2. Okay. So this kind of value we'll get for the maximum compression of the spring. Now think carefully what we'll get for the maximum value of VC.
So when X becomes 0.
Yes, very good. Okay. Because what's happening is that once this BNC system starts moving after having collided with A, what will be the situation of the spring? It will keep oscillating between compression and extension, because continuously that energy conservation is resulting in kinetic energy converting to potential and then potential reconverting to kinetic. Okay. So as long as the spring is compressed, it is pushing the block C. And the moment the spring extends, it starts pulling back the block C.
Yes, sir.
Okay, so how do we find the final, the maximum velocity of C? So we have to go back to solving that equation 1 and 2 that we are seeing over here, but under the condition that x is equal to 0. And when we put x is equal to 0, we'll be solving a quadratic equation which has a set of solutions. Okay, so one solution is, so I'll explain this. Okay, so the third part, VC's maximum value, how do we find that? So what we have to understand is that if the spring is compressed, then this is getting pushed. There's a force of kx acting on this like this, so it's having an acceleration. Okay. Whereas the moment the spring reaches a state of extension, eventually this starts decelerating. Okay, so at this point of time, this will be decelerating. So C accelerates while the spring is compressed, and C starts to decelerate when the spring is extended. So in between there is a time when the spring is at natural length. That is when C has reached maximum velocity. And then this whole cycle will repeat, because it's an oscillation. So if you get into the center of mass frame of B and C, you will see that VCM is constant. And with respect to the center of mass, B and C oscillate. So if we are at the center of mass, therefore traveling at VCM, what we'll see is that B and C, with respect to the center of mass, they go back and forth like this. They oscillate like this. Okay, Dhruv, to answer your question, okay, let's say, so Dhruv is asking why we are not involving the spring in the collision between A and B, right? So if we take this as t equal to 0, okay, then A and B are going to be in contact for a very short time, delta t. So after so if this is t equal to 0, after that time delta t is over, A and B have lost contact. Okay, so that time is so short that during this time, x of the spring is tending to 0. So spring force, so impulse due to spring, on both B and C is tending to 0. That's why we are not involving the spring. Okay, Dhruv, hope this point is clear.
Yes, sir. Got it.
So in comparison to how the spring behaves, the collision is a much faster event. Okay, practically speaking, let's say delta t is a microsecond or something, and the spring is going to take at least few milliseconds before it appreciably compresses. So that's why this is a much faster event compared to how the spring is behaving. Coming back to this, once the collision is over, Then if you start running along with the center of mass of B and C, you are moving at a constant velocity. But with respect to you, B is initially decelerating and C is initially accelerating. Okay. So this is what is happening in your frame. And eventually after some time when the spring starts extending, then this accelerates back, this accelerates back. So they have a back and forth motion. So you can see that the spring will alternate from x equal to 0 to maximum compression, x max equal to that value that we had calculated, which was whatever 5 by 6 v naught square root 2m by 3k. Okay, then back to x equal to 0. Okay, then back to maximum extension, and that maximum extension will also be the same. So we can actually solve this by without doing much calculation also. Okay, so one way of solving it is without getting into all that. So in the center of mass frame, center of mass of B plus C, which is traveling with that velocity, which was, now what will be the velocity of the center of mass of B plus C? It will be the common velocity when x was maximum. So that was how much? That was 1/3 of VB, no? So that was 5 by 18 V naught. Remember? This was the common velocity we had got in part 2. This V1 is equal to V2. Now, when we reach this is also the VCM of B plus C as a system. Okay. So if we are in that frame, this is how the situation looks. Okay. At t equal to 0, just after collision, just after the impact, at that point of time in that frame, we will see B coming towards us with a relative velocity and C also coming towards us with the relative velocity. Okay, and they will be at natural length. We'll see what that relative velocity is. Remember, in ground frame, what was VB? VB was 5 by 6 V naught. What was the velocity of the center of mass of B plus C as a system? 5 by 18 V naught. And what was the velocity of C? It's 0. So the velocity of B with respect to center of mass becomes this minus this.
Sir, to the
Yes.
center of mass, actually the center of mass will not be accelerating, right?
Yeah. So it's an inertial frame.
Yes, sir. So why would it seem to it that C is moving at a constant speed? C is accelerating and decelerating.
Because there is force, no? Look at the free body diagram. Spring force, no? So when the spring is pulling, or rather when the spring is pushing C, so at
Yes, sir.
this moment, actually, you know what is happening? C will have an acceleration like this with respect to the center of mass. And B will be having a deceleration like this with respect to the center of mass.
Yes, sir. So how will C have constant velocity with respect to the center of mass?
Constant velocity नहीं है बेटा. That's the instantaneous velocity at this moment. Oscillation हो रहा है ना with respect to center of mass.
Then sir, we've written above that it will have constant velocity.
Where we've written above, the center of mass has constant velocity, beta, not C.
Okay, sir. Okay.
Okay. So at this moment, what is the velocity of C with respect to the center of mass? It is minus 5 by 18 V naught. And this is plus 10 by 18 V naught. Okay. So this value here with magnitude is 10 by 18 V naught. And this value with magnitude is 5 by 18 V naught. Okay. Now from here, after some time, it reaches a situation where maximum compression is there. So at the moment there is maximum compression in my center of mass frame, how does the situation of B and C look? They have come closer, but also they have come to rest now momentarily in the center of mass frame.
Yes, sir.
Okay, they have come to rest. Okay, of course, my center of mass is moving at that velocity. Okay, so this is when they have come closest. They are at the maximum approach. Okay, now from here they will come back to this earlier position, natural length of the spring.
Yes, sir.
And by symmetry this time, when they reach that natural length position, what will happen? They will have the same speed but in the outward direction. So this time this V relative will be 5 by 18 V naught, and this V relative in this direction will be 10 by 18 V naught. Okay. Now can you tell me, out of these three pictures, in which one with respect to ground frame B is having maximum velocity?
So B.
No, in ground frame, which one B is having maximum velocity? This third picture, isn't it? Because
Yes,
what is velocity of C with respect to ground? It is velocity of C with respect to center of mass plus velocity of center of mass. No?
yes, sir.
So this is a constant value, which is how much? 5 by 18, right? V naught. This is the one which is variable. So when this reaches maximum value, this should also reach maximum value. Okay. So VC in the ground frame has a maximum value where VC of with respect to center of mass should have a maximum value plus this. So this is in diagram 3.
Sir, why can't we just solve the energy conservation and
But this is so much easier. No? I'm not solving any equation at all. You're seeing now, we can do the energy conservation and all that also. But here though, I'm not solving anything. I'm just looking at it in the center of mass frame and I'm using the symmetry. No?
Yes, sir.
Understanding the point? No? So this is actually like a shortcut way of solving this. No?
Yes, sir.
Okay. So actually at this point of time, they are having zero acceleration because the spring is at natural length. But here they are having accelerations in this direction. AC, AB. Then they're back to zero acceleration. Okay. And then next moment they will start decelerating. So these are the these are the extreme positions of the oscillation. Okay. When they are having maximum speed with respect to center of mass, that is picture 1. Then they are closest with respect to center of mass, that is picture 2. Then again back to maximum speed with respect to center of mass, that's picture 3. And from here, they'll go to a situation where they are furthest away. So when they are furthest away, they are again at rest with respect to center of mass. And this whole cycle of these 4 pictures will keep repeating. That's the oscillation. You know? But only this time they've reached extension, so they will have inward acceleration. They'll be coming back. Okay, so this whole cycle of 1 to 2 to 3 to 4 keeps repeating, back to 1, back to 2, like that. Okay, so from this we can understand that VC's maximum value will be equal to, now in this picture you can see V relative is 5 by 18 V naught, okay, plus 5 by 18 V naught. So it is 5 by 9 V naught. So this should be the maximum speed of C with respect to ground. Now we'll verify this from the energy equation also. And you'll see that when I convert it into a quadratic equation, the energy equation, I will not solve it as a quadratic equation because I already know one of the solutions of that equation. When x is equal to 0, okay, there are two solution sets now. One is what is happening just after the collision, and one is what is happening when it reaches the other extreme. That is, the spring has gone from the initial state to maximum compression and come back to natural length state.
So written.
Okay.
So just a minute, I'm still writing it.
Yeah, I'm waiting. Okay, done with this now.
Yes, sir.
Yes, sir.
Okay. So now see, there is another way of solving this without getting into full quadratic equation and all also. So just as we have understood this in the center of mass frame, we can also visualize this in the ground frame. Okay. Only in the ground frame we will have to write that energy conservation equation, but we already know one solution of it. Okay, so we won't really need to solve it that way. So we are seeing this with respect to ground. Okay, so just let's say the collision has just occurred just now. So this has got that velocity of whatever it was, v naught by 5, right? Or how much was it?
V naught.
After collision, just after collision, how much it was?
V naught by 3.
V naught by 5, no? Or
No, so 6.
v naught by 6, okay. And B's velocity was how much? 5 by 6,
Yes, sir.
right? So this is A, this is B, and the spring is in natural length. Okay, so X is 0 and this is at rest at that moment. Okay. Now from here, after some time, it's going to a situation where maximum compression and all that has happened. And now after that, it's come back to natural length. So this is the situation when C's velocity is becoming maximum now. When it's back to natural length. Okay. And in between these two, you're having that maximum compression situation. So that time VB was equal to VC. Okay. Now VC has reached its maximum value, and this has some different value. Right. So if we compare this and this, okay, so you can see that for B plus C plus spring as a system, linear momentum is M into 5 by 6 V naught plus 0 in this case, right? And that is equal to, in this case, M into VB plus 2M into VC, where this has reached its maximum value.
Yes, sir.
That is one equation we have. Okay. And also the mechanical energy of the system, which is half M 5 by 6 V naught whole square plus 0 plus 0. Okay, no potential energy here. That is equal to half M VB square plus half 2M into VC's maximum value squared plus 0. Okay. So if you now compare equation 1 and 2, it's which type of equation actually? It's again a perfectly elastic collision between B and C, isn't it?
Yes, sir.
Again, it's like, the spring has played the role of initially storing some potential energy going from here to here, and then again releasing that potential energy. Okay. Going from this picture to this picture, the change in potential energy of the spring is equal to positive of the maximum potential energy. And then going from here to here, the spring is again losing that potential energy now. You understanding the point?
Yes, sir.
So can't we solve this directly by formula now? Okay, so solve it directly by formula to get VC max and verify it's the same answer.
Yes, sir, it gives the same answer.
So we can avoid solving these two equations because, so from equation 1 and 2, you can see that VC max will be like that second body's velocity. So that is 2 into m1 divided by m1 plus m2 into the initial velocity of this one, which was 5 by 6 v naught. So that is 2 by 3 into 5 by 6. So 5 by 9 v naught. So VC's maximum value is equal to 5 by 9 v naught. Or another way we could do this is that, when we look at this equation, so what we're getting 25 by 36 v naught square is equal to VB square plus 2 times VC max square. Okay. And we have this equation, which is 5 by 6 v naught is equal to VB plus 2 VC. So if we substitute this over here, okay, so let's take VC max as a variable x. So 25 by 36 v naught square is equal to VB, which is 5 by 6 v naught minus 2x whole square plus 2x square. So we want to solve for x. Now we already know that one of the roots for this is x equal to 0 is one root. Okay. So the other root will come out to be 5 by 9 v naught. And that is our VC max. You can see in this equation that, the constant term will cancel on both sides. 25 by 36 v naught square. So it will be that kind of quadratic equation which has one root 0 and one root positive.
So done.
Yes, very good. Okay. So you can see, this is that second root which will give you the V. So once again, you can see after the collision between A and B is over, there is like a slow motion collision happening between B and C till C reaches its maximum velocity when X is 0 again. And then again, C drags the spring with it. So the spring goes into extension, okay, reaches maximum extension. By that time, B is approaching C. So from maximum extension, the spring again starts relaxing, comes back to natural length. And we are back to square one. We are back to this picture when spring comes back to natural length. So from here, it will go to a state where it's at maximum extension instead of maximum compression. And then from there, it is back to the first picture. At that moment, this will be 0. And when it reaches maximum extension also at that moment, VB will be equal to VC, which will be that 5 by 18 V naught. So in a later chapter, simple harmonic motion, we learn to find the time period for this cyclical motion also.
So how many chapters are left?
For what?
The 11th.
For 11th, we have oscillations and waves. You are currently doing heat and thermodynamics, right?
Yes, sir.
And we have rotational mechanics.
So gravitation?
Gravitation we will do along with electrostatics actually, because the two are combined. I mean, the two are like gravitation. The first part of gravitation is common with electrostatics in structure. So though that is part of your technically your 11th syllabus, but we'll be doing it alongside with electrostatics in 12th. You'll have few board lectures for 11th of gravitation, so that you can deal with it at your term exam level. Okay, but for JEE we'll do it along with electrostatics because it's a waste of time and energy to do it separately.
Okay, sir. So return.
Okay, this is clear.
Yes, sir.
Okay, now let's look at another situation where we'll use concepts of center of mass and system of particles. So once again, we have a smooth surface, but this time on the smooth surface, we have placed a pretty long plank kind of thing. Okay. And the top surface of the plank is rough. Okay. So this is a smooth surface, but this has a coefficient of friction mu. And basically this is a plank of mass capital M like this. Okay. Now on top of the plank, we have placed a comparatively very small block of mass small m. Okay. And what we do is to set the system into motion, we apply a sharp impulse on this. So like it's almost something is coming and hitting this with a sharp collision and setting the top block into motion initially. So initially the system is at rest and at t equal to 0, a sharp impulse. So sharp impulse basically means that very large amount of force is acting for a very short time delta t. Okay. So sharp, something like a collision impulse. J equal to, let us say, 0.6 Newton seconds is applied on the block. So given the mass of the block is 3 kilograms and the mass of the plank below, that one is, let us say, 7 kgs. And coefficient of friction is 0.5 and G is 10 meters per second square. So assuming the block comes to rest with respect to the plank, okay, and does not slip over the edge. So the plank is long enough. has a sufficient length for that. So with this assumption, we want to find the final velocities of M and capital M when slipping stops between them. We want to find the percentage loss of kinetic energy dissipated by friction. And the impulse due to friction on the block and on the plank. What is the net impulse that friction applies on the block and the plank? Just try this out, people. Anyone got the answer?
Yes, sir.
Yeah, tell me. How much is the final velocity coming out to be?
Just 6 centimeter per second.
Yeah, it will be 0.3 times this, no? The initial velocity. And initial velocity you can get by just dividing the impulse by the mass, isn't it? Of the block.
Yes, sir.
So 0.6 divided by 3. So that is 0.2 meters per second. Okay. And this will become 0.2 into 0.3. So 0.06. Yeah. So 6 centimeters per second. That is correct. Okay. So again, the thing is, the impulse is a sharp impulse. So while that impulse is acting, you can ignore the friction acting between the block B and the plank, even though actually friction starts acting just as the force F starts acting for that time delta t. But the time delta t is very short, whereas the frictional force's value will be much smaller compared to that capital F, because it's not a sharp impulse because of friction. You understanding my point now?
So not really.
Okay, so see what is happening is while this force F is acting for that short time delta t, friction starts acting then itself, because slipping starts. But we can ignore friction compared to that F. When you start applying this force, this is from t equal to 0 to t equal to delta t. So while that time friction is also acting, okay, like this. But delta t is very short. Okay, and F will be very large compared to friction. So we can ignore the effect of friction. From 0 to delta t that time. So what we can do is we can treat it like two independent events. T equal to 0 to t equal to delta t. Just treat it as if there is one impulse acting on this and no impulse acting on this. So at delta t, this starts moving with a velocity v0, and that j is equal to mv0. So this one's initial velocity is j by m, which was, how much was j? 0.6, no?
Yes, sir.
Divided by the mass, which was
3.
3 kgs. Okay. So this v0 is 20 centimeters per second or 0.2 meters per second. Okay. Now friction comes into play. Okay. Once this event is over, this sharp impulse acting on this, now you start taking the effect of friction, because friction acts over a sufficiently long amount of time. Okay. So friction starts to decelerate this and to accelerate this. Okay. And starting, so in general, at any time, this is V1 and this is V2. So initially, that is at t equal to delta t, which is almost t equal to 0. Okay, yeah, V1 is V0 and V2 is 0. And after sufficiently long time, they are having a common velocity. That is when slipping stops. So when slipping ceases to exist, okay, V1 becomes equal to V2 becomes equal to Vf. And that's when friction stops acting. Friction also ceases to act. Okay. So they are going at a common velocity. So now the interesting thing is, if you look at this picture and compare it to this picture, for the system there is momentum conservation because the external force is 0. So for
Yes,
m plus m as a system, okay, after the impulse j has been applied, because that was an external impulse, but eventually, okay, so in fact that external impulse only will be equal to this momentum, which will become equal to this. That's another way we can calculate the final velocity, by just equating the final momentum of the system with the net impulse from the beginning, from t equal to 0 onwards. So this final speed will just become, so we don't need to calculate the acceleration, deceleration, involve time and all that, kinematics. All those steps are not required here. This is actually like an inelastic collision. This moving object at mv0 is giving some impulse to the larger object capital M via friction and receiving some equal and opposite impulse. Still what happens? Both of them become one body moving at a common velocity. So it is very much like an inelastic collision, perfectly inelastic collision. That kind of result we are getting over here. So this final common speed is becoming 3/10 or 0.3 times this. So it becomes 6 centimeters per second. Okay. And then you can calculate the impulse acting because of friction. So impulse acting because of friction, you can write it as such that minus of that impulse is equal to mvf minus mv0, or plus of that impulse is equal to capital mvf. Both ways you'll see it's the same, and you'll get the magnitude of this impulse equal to 0.42 Newton seconds. Okay. As far as the percentage energy dissipation is concerned, the initial kinetic energy before friction starts acting is this much. Okay. And the final kinetic energy is so this is so percentage loss will be this much. I think it's a 70% loss now. Okay, so people hope this concept is clear. So we have another
Yes.
session coming up day after tomorrow, I think. So we'll discuss further about some more applications of this type for eventually getting into variable mass systems. So that's it for today's session, people. Wish you all the best and have a nice day.
So what
Thank
about
you, sir.
homework?
Bye, sir.
Thank you, sir. Yeah, do questions from the module, okay, and I'll also send a revision worksheet for collisions soon.
Okay, sir. Thank you, sir.
Okay.